Okay. Yes, good morning friends, welcome back. Yesterday there was a break for the presentation, so in the middle we have stopped the Simpson's 3/8 rule. Now once again, let's recap what this Simpson's 3/8 rule is, because we have stopped in between. So the rule is derived by approximating f of x by a third degree polynomial. As I said, third degree polynomial passing through 4 points. Trapezoidal rule is first degree approximation of function by first degree polynomial, that is a straight line. Then Simpson's 1/3 rule is approximation of the function f of x by second degree polynomial passing through 3 points. And Simpson's 3/8 rule is the rule derived by approximating f of x by a third degree polynomial passing through 4 points. So when I take 4 points, how many subintervals? Possible value of the number of subintervals, we can have 6. 1, 2, 3, 4, 5, 6. Then how many points we have? 1, 2, 3, 7 points. 3n plus 1 point, 7 points, or 6 subintervals. 3n subintervals, or else number of points is 3n plus 1. When that is the case, the Simpson's 3/8 formula is given by integral a to b f of x dx is equal to 3h by 8, where h is step length, into y0 plus yn, the first point and last point, on the point ordinate, first ordinate and last ordinate, or the value at the first point and the last point, plus 3 into y1 plus y2, y4 plus y5, so on and so forth, yn minus 1, plus 2 into y3 plus y6 plus, so on and so forth, yn minus 3. So this is called Simpson's 3/8 rule. Only condition that we have to remember is number of subintervals is 3n in case of 3/8 rule, and in case of 1/3 rule, the number of subintervals must be an even number, 2n. There it is 2n, it is here 3n. Trapezoidal rule, there is no condition on that. So evaluate integral 0 to 1 square root of 1 plus x power 4, square root of 1 plus x power 4 dx. So because we want to apply Simpson's 3/8 rule, the let's say we divide this into 6. At 1 by 6, the functional value is 1.00038. Then x is 2 by 6 because h is 1 by 6. F of x is 1.0061. Then 2 by 6 plus 1 by 6, that is 3 by 6. The function value is 1.03, and 3 by 6 plus 1 by 6, 4 by 6. So the function value is 1.0943, so on and so forth, like, okay. So the integral value is, we got all the values, required values now. 3 by 8 into h is 1 by 6. The first value plus last value. First value is 1, the last value is 1.4142, plus 2 into y3, y6. Name them as y0, y1, y2, y3, y4, y5. y0, 1, 2, 3, 4, 5, 6. So y6 already we have considered here, no need to consider. So y2 is the only term that we have. So that is this one, 1 point, y0, y1, some mistake. Yes, y3, yes, 1.03. y0, y1, y2, y3. 2 into y3. So 2 into 1.03. We need not consider y6. We have already considered here 414 type. So 3 into y1 plus y2. 3 into 1.00038 plus 1.0061. This is already considered here. So this is 1.0943 and 1.274. So weighted average of this, if you take comes out to be 3 by 48 times 17.4307, and the value of this is 1.08942. This is how, see, 0 to pi by 2 e power sin x. So again, I take h is equal to 1 by 6. So b minus a by n, if I take n subintervals, then pi by 2 by 6 is pi by 12. So x value 0 to pi by 2, 2 pi by 12, 3 pi by 12, 4 pi by 12, 5 by 12, 6, and 6 pi by 12, that is pi by 2. So then e power x sin x values are tabulated like this. So 3 by 8, h is h by 12, sorry, pi by 12. Do y01 plus y6, that is 2.7183, plus 2 into y0, y1, y2, y3, 2 into y3, plus again y6 should be there, but is already considered last point, there is no need to consider this, plus 3 into y1, y2, 1.2954 plus 1.6487, then 2.3774 plus 2.6272. If you calculate this, you get 3.1043 as the answer. So that's what we do in numerical integration, Simpson's trapezoidal Simpson's rules based on Newton-Cotes formula. Now we will go to the next idea in numerical method, that is numerical solutions of ordinary differential equations. So actually we don't solve ordinary differential equations here, we consider initial value and boundary value problems. What is an initial value problem is? Initial value problem is a differential equation along with an initial condition on the solution, like y of x0 is equal to y of 0. So here you see y dash is equal to f of xy, y of x0 is equal to y0. This is what we call a initial value problem equation. What is given here? On differential equation of first order first degree, because here we study only, we restrict ourselves to first order first degree equations. So we study this differential equation of the form y dash equal to f of xy, satisfying the condition y at x0 is y0. Such a problem is called initial condition. The total differential equation along with initial condition is called initial value problem. We consider the initial value problem. So numerical solutions of differential equations. This is what we are going to study. So in differential equations part, what we have studied is we have expressed y of x is equal to C1 y1, say for example higher order equation, second order differential equation with constant coefficients. We express y as a sum of complementary function plus particular integral. So y is complement and yc is a complementary function involving arbitrary constants, and particular integral does not contain arbitrary constants but correspond to the function p of x. We are calculating particular integral. All said and done, what is that we did in differential equations is we try to express the solution y of x as a function of x explicitly. That means clearly y is equal to so and so is the solution. So it is called a closed form solution or finite form of solution. It is called closed form solution of a differential equation. The solution of a differential equation y is expressed as a function of x explicitly, then it is called as the closed form or finite form of solution. So this is what we did in differential equations is closed form solutions. But it need not be possible always to find the closed form solutions because of different things involved in the problem. Maybe the f of xy may be very, very complicated. So, and the structure of the differential equation may not allow you to write it as a the solution as a explicit form of the independent variables. So many aspects are there. for not being able to write that equation, solution of the equation as a explicit function of the independent variable. There are so many reasons for that. Anyhow, in the absence of such a solution, whatever be the reasons, if you are not in a position to calculate the closed form solution, then we resolve to solve the solution using numerical methods. So this process of finding a solution using numerical methods is called a numerical solution of differential equations. Here there are very basic, some few basic methods that we have in our undergraduate study. One is Taylor series method, and the other one is Picard's method, Euler's method, modified Euler's method, Runge-Kutta methods. There are n number of methods like this. If you go on naming, so list is too large. But we have taken 5 basic methods, and these 5 methods also differ from one another. So each one is an example for a class of solutions that we try to get. So here we consider the initial value problem. Let us see what is the difference between one method and other method. Here we consider the initial value problem. Y dash is equal to f of xy, yx naught is equal to y naught. The solution obtained is in one of the following forms. What are the type of problems, the solutions we are getting, structures of the solution, different forms of the solution we are getting. We are getting a series in x sometimes. Sometimes whatever solution we get for this initial value problem, that will be like a series in x. That is called, say for example, a0 plus a1x plus a2x square plus a3x equal a series. It may be a solution. So out of these 5 methods, the first 2 methods, Taylor series method and Picard's method, they give a series solution, or else in that method we get the solution as a series in x. So those 2 methods are called Taylor series method and Picard's method. The remaining solutions like Euler's, modified Euler's and the Runge-Kutta methods, we get a set of tabulated values of y corresponding to different values of x. So corresponding different values of f, if you calculate, you get the solution as a value, a number at a given value of x. Like if y of 0 is equal to 1 is given to you in the problem initial condition, then you will get y at 0.1, you will get y at 0.2, y at 0.3, y at 0.4, so on and so forth. So if you solve, we set up a set of tabulated values of y corresponding to different values of x, different values of the independent variable will be obtained. So in this last 3 methods, Euler's method and modified Euler's and Runge-Kutta method, is what happens. And in the first 2 cases, we get a series in x. Both the methods have their advantage and disadvantage. So once you get as y as a series, a0 plus a1x plus a2x square plus a3x, so on and so forth, then the advantage is you can get any value of y at any point of x. So when we have y of x is equal to a0 plus a1x plus a2x square, put y x is equal to 0.1, you get y at 0.1. If you get x is equal to 0.2, you get y at 0.2. If you get your x is equal to 100.2, you get y at 100.2. For any value of x, you will get y of x. That is one major advantage in writing the solution as a series or a explicit solution. So the other way is in the set of tabulated values, the calculation part is less, but if I get the value y at 0.1, that's all. If you want to get at again y at 0.2, go back and do it again. So that is the difficulty involved. But because it is it's a numerical methods, it's simulation, and if you write a program and run it on the computer, it takes very less time to evaluate the functional values at different points. So those are the main difference between these methods. Let us discuss one by one methods, one after the other. Taylor series method. This method, as the name suggests, is completely based on Taylor series expansion of a function. Taylor series expansion of a function. So consider the IVP given by 1. Okay. Let us say if y of x is the exact solution of 1, then the Taylor series of y of x around x is equal to x naught. If you go back and recollect what is Taylor series, y of x is equal to y at x naught plus x minus x naught into y dash x naught plus x minus x naught whole square by 2 factorial into y double dash x naught, so on and so forth. X minus x naught power n by n factorial yn at x naught. So this is Taylor series about x naught. So what are the different things that we don't know here? X naught we know. Y, the problem is given as f, y dash is equal to f of x y. The initial condition x naught we know, and the corresponding value of y at x naught is also known, that is y naught is also given to you. Now knowing this, y of x naught, you know it, x minus x naught you know it, x is a very independent variable, y dash x naught you know it. It's not directly given the problem, but you know y dash is equal to f of xy. Okay. If you substitute x naught, y naught in this, you get y dash at x naught. Then here coming to the third term, x naught, 2 factorial, everything is known. Only thing that we don't know is y double dash x naught. The next time y triple dash, then y fourth derivative of y, so on and so forth. These terms we don't know. And we have to derive the expressions for y double dash, y triple dash, so on and so forth from the given differential equation y dash is equal to f of xy. Then what is y dash is equal to f of x? If y dash is equal to f of xy, then what is y double dash? That is d square y by dx square is equal to dy dx of dy by dx is equal to dy dx of f. Dy by dx is equal to f of xy. So dy dx of f of xy, that is dou f by dou x plus dou f by dou y into dy by dx. This is what we have the equation. Standard result, this is we have total derivative concept. So d square y by dx square is equal to dou f by dou x plus dou f by dou y, that is fy into f, because dy by dx is equal to f. So that's your d square by dx square. Again, if you differentiate this, derivative of this fx with respect to x, this with respect to y, so this becomes d by dx of f of x plus d by dx of f of y into u into v formula, df of y into f plus fy into df by dx. This is u into v formula that we apply. So this is again a function of x and y. So we have to write this total derivative, d by dx is total derivative. That is what happens, fxx into dou f by dou xyf into f. Similarly, these are the expressions that we get. So simplify this, we get fxx plus 2fxy plus f square fyy plus fx into fy plus fy square f. So that is the second derivative, third derivative of f with respect to x, and so on. So you then substitute this x is equal to x naught and y is equal to y naught in these expressions. You will get all the terms involved here, y dash x naught, y double dash x naught, y triple dash x naught, so on and so forth. So for that you have to calculate these things first. Okay. Then try a problem on Taylor series method. Y dash is equal to x square y minus 1 and y at 0 is equal to 1. Find the solution as Taylor series and find y at 0.1. So clearly x naught is equal to, because y at x naught is 1, so x naught you have taken it as 0 in the problem, given as 0 in the given problem, and y naught is equal to 1. So with this, y dash is equal to x square y minus 1 given in the problem. So y dash 0 is minus 1. If you put x naught is equal to 0 and y is equal to 1, this becomes 0 minus 1. So what is y double dash x? That means this is y dash. If you differentiate again with respect to x is u into v formula, because y is a function of x square into derivative of y, dy by dx, that is y dash, plus y into derivative of x square 2xy. Okay. Y triple dash, again differentiate this with respect to x, apply uv formula wherever is applicable. So x square into y double dash plus 2x into y dash. That means first x square into derivative of this y double dash. Then y dash into derivative of this is 2x plus again same way 2x into derivative of y dash plus y into derivative of 2x is 2. Y into derivative of x is 2y. So d fourth derivative x square into y derivative of y double dash y triple dash plus 2x into y double dash. This is over. Coming to this 2x into y double dash plus y dash into derivative of 2x, that is 2. This one. Coming to this. So like this you go on finding the different derivatives. Y double fourth derivative at 0 is equal to, you get minus 6. So put these things in the Taylor series expansion. So y of x is equal to y x naught plus x minus x naught, because x naught is 0, x naught becomes 0, into x into y dash plus x square by 2 factorial y double dash, so on and so forth. So if you put the values of different things that you have calculated, you get this as a solution. And finally find y at 0.1 as 0.80227. This is how we solve these problems using Taylor series. How we solve differential equations along with initial conditions using Taylor series method. Taken that problem, y dash is equal to 2y plus 3 e power x, y at 0 is equal to 0. Find y at 0.2. So y dash is, if you put these things, x naught is 0, y naught is 0. So this is 2 into y naught is 0, 3 into e power 0, because x naught is 0, that is 3. So y double dash is 2 into y dash plus 3 e power x. Y triple dash is 2 y double dash plus 3 e power x. Y fourth derivative, so on and so forth. Get all these things at x naught. So y double dash becomes y dash x naught. Y dash x naught is 3. That is 3 into 2, 6. Plus 3 into e power 0. That is 3 into 1, 3. Total 9. So y triple dash is 2 y double dash plus 3 e power x. So y double dash, y dash is, okay, if you put this y double dash here at 0 here, that is 9. So 2 into 9, 18, plus 3 into e power 0 is 3 into 1. So 18 plus 3 comes out 21. Again differentiate, you get 45. So put all those things in the given Taylor series. I have 0 plus x into y dash 0 plus x square by 2 factorial y double dash 0, so on and so forth, which is the Taylor series about 0. So then I want the value of the solution at 0.2. So if you substitute that at 0.2, we get 0.8110. This is the root, the solution at y equal to 0.2. Now, if you have an interval AB, let us say 0 to 10, and h you are taking, let us say 0.1 or 0.2 you are taking h. So how many values you have to run for h when you want to cover from 0 to 10? And if you take h is equal to 0.1, 100 values you have to take. So up to 0 to 1 we get 10 values. Like that, 0 to 100 we get 100 values. So how many times you have to calculate this? H equal to 0.1, the second point is 0.2, 0.3, 0.4, 0.6, 0.7, 1.3, 1.4, 1.5, 2.7, 2.8, like that. So we have 100 values of h, and not h, the values of x, and you get y xi at all different points. Obviously, what happens is when h is very, very small, if you want to find the value of the function at xi in interval like this, it becomes difficult because it goes very slowly. It covers the interval very slowly. Next method is Picard's method. Picard's method is also, as we discussed earlier, it is a series solution method. It also gives a solution as a series in x. Let us say y dash is equal to f of xy, yx naught is equal to y naught. Here we take a very different turn in the process. There we used Taylor's theorem, but here we are not doing so. So straight away integrate with respect to x between the limits x naught and x. Because why x naught? Because the initial point we know it is x naught. So integrate between x naught to x y dash f of x y. So yx minus y naught, yx naught becomes 1. Okay, so if you integrate this, y at x minus y at x naught is equal to integrate x naught to x f of x y dx, or y of x is equal to y of x naught plus integrate x naught to x f of x y dx. This is the base idea of Pickard's method. But the question now is, what is the unknown? We want to calculate y of x. That is the unknown. Okay, and we have an expression to calculate the unknown. What is the expression? We have an integral term on the right hand side. What is there in the integral? F of x y. Do you know why? No. This is what we are finding. Y is what we are finding, and in the integral again we see y. Can you integrate this term now without knowing y? Cannot do it. You cannot integrate this function as long as y is inside the integral. So this is a very typical example in numerical methods. This type of things, the unknown comes under some particular operation very frequently. Here it comes under integral operation, the unknown. So how we deal with this is initial approximation methods or iterative methods. Whenever the unknown value or dependent variable appears on both sides of the is equal to, both sides of the equation, the left hand side and the right hand side, then usual methods fail. We have to go for numerical methods. So as a first approximation of y, let's say y1 is equal to y naught plus integral x naught to x f of x y naught. So what we do, what we are doing, because if we cannot integrate this, let us approximate this y by the initial condition, whatever we have, y naught. In place of y, you put y naught. It will not, because call the result as y1. So y1 is given by y naught plus integral x naught to x f of xy. In that place, you take f of x y naught. Yes. So nth derivative is yn plus 1 is equal to y naught plus integral x naught to x f of x y of n dx. So this is the scheme for the Pickard's method. This is scheme for the Pickard's method. Yn plus 1 is equal to y naught plus integral x naught to x f of x yn. Okay. So question now, when n is equal to 0, we get y0. This y0 is obtained from the given problem, taken from this y naught. So you put this y naught here, you will get y1. Put y naught, you will get y2. Put y2 here, you will get y3. So like that, if you put yn here, you are getting yn plus 1. Here, yn is nth approximation of the solution at x is equal to x1. So do a problem and understand easily. Y dash is equal to y plus x, y at 0 is equal to 1. Find the solution of a third up to third degree term. We have to calculate the solution up to third degree term. So the first thing, that is y1 is equal to y0 plus integral x naught to x plus y of z, because the function is f of xy is y plus x or x plus y. I write this as x plus, in place of y I am taking y naught. That is initial approximation. So 1 plus integral x naught to x plus y0 is 1 dx. If you integrate this, 1 plus x squared by 2. So y2 is y naught plus, put this y1 here inside this integral, then call it as y2. So y2 is equal to y naught plus integral x 0 to x, y0 because integration from 0 to x, x plus y1, x plus y1. Calculate y1 is already known to you. You put this y1 here, so x plus 1 plus x squared by 2, x plus 1 plus x squared by 2 dx between the limits 0 to x, that becomes 1 plus x square plus x cube by 6. So that's how we go ahead with increasing n. Finally, this x1, x2, so on and so forth, the xn, they converge to the actual solution. So, y dash is equal to 3 minus x square, y at 0 is equal to 1 by Picard's method up to 4th degree term of x. Up to 4th degree term of x we have to calculate. Okay. So, this is the one way of asking the questions. You will be asked to find the solution of this so-and-so equation. Y dash is equal to y minus x square, y at 0 is equal to 1 up to 4th degree term is A. 1 plus x square by 2 minus x cube by 3 minus x power 4 by 12. B. 1 plus x plus everything, all the options look like the same. That is to trap you, to put you under pressure. Okay. So, very clearly, sometimes you miss positive and negative signature signs. In place of positives, we use negatives. In place of negatives, we use positives. So, be very careful with that. You may be asked to find the fifth term of this series expansion of y of x. Okay. In that case, we have to be very careful. So this is a type of questions. Integrate this, we get y of x, that is x of t. Again, you put it in the form y0 plus integral 0 to z, 0 into 0 into x dx. That comes out to be 1 plus 0 to x, 1 plus x minus x cube by 3 minus x square dx. That is 1 plus x square by 2 minus x cube by 3 minus x power 4 by 12. This is how we use the iterative methods to find the solution y in terms of x as a series. And that problem, y dash is equal to x square plus y square, y at 0 is equal to 1 up to second approximation. So call that because y1 is y0 plus integral 0 to x square plus 1 dx. So if you integrate that, because y1, because y0 is 1, we are using it y0. So that if you integrate this 1 plus x cube by 3, then y2 in place of y you substitute this y1, and y0 plus integral 0 to x square plus y square is y1 square. y1 is this one, 1 plus x cube by 2 whole square dx. So expand that and solve this, you get y of x is up to x power second term, because we have y square. If you have 1 plus y x square term, will be x power 6 x power. Okay. So this is series solution that we get. That is a Picard's method. And then the third method is Euler's method. In Euler's method, what we have is they don't give you series expressions. They give directly the tabulated values of the dependent variable. They don't give you any functions. They clearly give you functional value of the solution at the required point. Whatever point you ask, x is equal to 0.1, 0.2, then this directly the calculation gives you value of the solution at a given point. So basically in Euler's method and the methods beyond here, after this, we don't get the closed form solutions or finite form solutions. We get the solution as a data or tabulated values of the solution at different values of the independent variable. So if the equation is y dash is equal to f of xy and y of x naught is equal to y naught, that is, if y is equal to g of x is the solution, then y dash depends on the slope. Say for example, solve the differential equation y dash is equal to f of xy. Let us say, if you know the solution, that is, let us call the solution as y is equal to g of x. Okay, it's a curve, it's a continuous curve. It must be a continuous curve because we have already defined y dash on that. So, this is a continuous curve. If you want to find this tangent to at any point of this y, then you must need the slope of the tangent that is given by y dash or g dash x. and the given point is this point x0 y0 is already given. If you from this curve, if you find this slope, then the point slope form of the tangent is y minus y0 into slope at x0, that is y dash at x0 into x minus x0, or y is equal to, if you send this y0 here, y0 plus, what is y dash? Y dash is f of xy at x0, f of x. So f of x0 at x0, what happens to y0? Y0. So this becomes x minus x0 into f of x0 y0. This is the equation of the tangent. Okay. Now if I put x is equal to some x0 plus h, with some nearby point, x is some nearby point of x0. That means these 2 points differ by a constant h. So then x is equal to x1 is equal to x0 plus h. Then x minus x0 will be equal to h. So y at x1 will be y1. We call it as y1 is equal to y0 plus this x minus x0 will be h into f of x0 y0. Or else similarly we get y of x. This is first value. Similarly, you use this. Now the new point is x1 comma y1. If you calculate, you get y1. Call it as y of x1 as y1. That point then is x1 comma y1. What is the first point? x0 y1. Second point x1 y1. Now similarly, use this point to get y of x2 as, repeat the formula for this point. At this point x1, y of y1 plus integral y dash x minus x, something like that. So we get y1 is equal to y0 plus h into the very similar lines. In the very similar lines, y is equal to y0, try to get the tangent at y1, that is given by y minus y0 is equal to h into f of x0 y0. Or if you bring the all similar terms to the other side, so y1 becomes y0 plus h into f of x0 y0. So given that x0 y0, we are getting the value of y at x1 y1. Okay. Similarly, we get y of x2 is equal to, generalize this. So y of xn will be equal to yn minus 1 plus h into f of xn minus 1 yn minus 1. This is called Euler's method. This is a single step method. You would understand that it's a single step method. What do you mean by single step method? So if you see this expression here, yn is equal to y at xn is equal to yn minus 1 plus f into x n minus 1 y n minus 1. So to find the value of the solution at y at xn, how many previous values we are considering? N minus 1, it is n minus 1, n minus 1. So if you want to find y at xn, the only thing that we are using is the values at one step backward. That means at n minus 1 level. So that's why using all the values at n minus 1 level, we are getting the values of y at nth level. So that's what is called single step method. We are considering only at this n minus 1 level, and then we are calculating the value at nth level. So it's a single step method. So what are the merits and demerits? What are the merits and demerits? So merits and demerits, coming to the demerits, this is x is equal to, assumed to be x1 is equal to x0 plus h. That means h is very, very small thing. H is very, very small thing. When h is very, very small, what happens? Let us say this differential equation is defined over integral a b 0 to 10. Okay? If you want to find the values in the interval 0 to 10, and if asked you to calculate all the solution about the interval 0 to 10, then h is very small. If you take 0.1, then how many values of h to take? 0, 0.1, 0.2, 0.3, 0.4, 0.5, 100 values you have to take. So the process is very simple. H must be very small for more accuracy. So solution cannot be improved. That is one more disadvantage. Need not calculate derivatives. That is an advantage. Slow method. So the benefits are very simple and need not calculate derivatives. These are the two advantages. Very simple method. You need not find f dash values at any point, just like in case of Taylor series. But the problem is, for more accuracy, if you reduce the value of h, the increment length, step length is, if you reduce the step length, that means what happens? the number of points will be more, becomes more complicated, lengthy problem. So, and the third one is, once you get y at 0.1, this cannot be further improved. That's all. If you get y at x1, then it cannot be improved. That is the problem. One more thing here is the slope y dash at x naught is approximated only as f of x naught y naught. That is one advantage. We'll see the next method, we'll understand it better, how this can be improved. Let us say solution problems. Y at 0.1, find y at 0.1 and y at 0.2. Given that y dash is equal to x cube plus xy square into e power minus x. Given that y at 0 is equal to 1. So y at 1 is equal to the formula we have is y at x1, we call y1 as y naught plus h into f of x naught y naught. So y at 1, that is y at 0.1 is h, y naught. What is y naught? It is given in the problem. Plus h. What is h? 0.1. How do you get h from the problem? Not given directly in the problem. How do you get h? See, what is given? Y at 0 is given. And what they are asking you? They are asking to correct y at 0.1. So 0 and 0.1, what is the difference? That is 0.1. That you take as h. So 0.1 into f of x naught y naught. F of x naught is 0, y naught is 1. So f of x naught y naught is f of 0, 1. If you put x is equal to 0 and y is equal to 1 in this problem, what we get? 0, and this becomes 0. Okay, everything is 0. F of 0, something. So this expression goes out at what of, but y of 0 is equal to 1, that is there. So your y1 is 1. Coming to y2, that is y at 0.2. Y at 0.2. So what is yx1 here? Whatever value you have got y1 here, that one we take it here. Plus h is, you are asking about 0.2. So y at 0.1 and y at 0.2. But 0.1 and 0.2, what is the h? 0.1. So h is 0.1, f of x1 y1. Now it is f of x1 y1. What is x1? 0.1. What is y1? 1. So if you solve this, you get 1.0091. Take another problem. Y dash is equal to y minus x by y plus x. Y at 0 is equal to 1. Phi at 0.1 and y at 0.2. So because from the problem x naught is 0, y naught is 1, h is 0.1. So y1 is equal to y naught plus h into f of x0, y0, x0 is 0, y0 is 1. So you calculate this, it is 1.1. And y2, while calculating y2, the previous level, that means x1 and y1 come into picture. Only x1 and y1. So this y1 is 1.1 plus h is 0.1 into y1 minus x1 by y1 plus x1. This is called 1.1 plus 0.1 into 1.2. You calculate, you get the value of that. So this is a very simple method known as Euler's method. A single step method. We are getting y at xn plus 1 using the values of y at nth level of the calculations, right? So that is Euler's method. So then what is this modification? What is this Euler's method? Modified Euler's method. As said earlier, here the slope of the straight line is that tangent is approximated at the point x naught y naught only, y dash at x naught y naught only. So to improve the solution, let us see what is done here. In Euler's method, y1 is equal to y naught plus h into f of x naught y naught. Here the slope is approximated by one point at x naught y naught. So y dash x naught becomes f of x naught y naught. So if the slope of the tangent x naught y naught is approximated as an average of the function value at 2 points, it is x naught y naught and x1 y naught. Improvement. So what happens then? Y dash at x naught y naught is f of x naught y naught plus f of x1 y1 by 2. So we put it there, the slope term here. What is that? This one. So in place of f of x naught y naught, we substitute that. Okay. So y of x1 becomes y1 is equal to y naught plus h by 2 into, in place of f of x naught y naught, we get these two things. Okay. And y1 is unknown. And if you see this term, y naught is known, h is known, x naught y naught is known, x1 is known, y1 is not known. Y1 is not known. That is the problem. So on the right hand side we have y1, on the left hand side also y1, and y1 we don't know. So let us call, as I said earlier, whenever you know Picard's method, whenever you don't know anything, the unknown is there on both sides of this equation, then we have to go for approximation method. So because y1 is unknown and it's there in this operation also on the right hand side, let us say initially it is equal to y10 is equal to, just like we have approximated an initial approximation Newton-Raphson method, here we assume that y10 is y1 from Euler method we use here. So whatever value you want to get y1, first you get it from Euler's method. So why that we call that as y10. Calculate y1 from Euler's method and we call that as y10. And then replace this y1 by y10 here and find y11. The first approximation notation is very important. y10 is the approximation of y1. y1 means y at x1. So y11 means first approximation to y1. y12 is second approximation to y1. And y1n is nth approximation to y1. So y11 becomes y0 plus h by 2 into f of x0 y0 plus f of x into y10. How do you get y10? y10 is obtained from Euler's method. This y10 is y0 plus h into f of x0 y0. So if you, because this is known to us now, so if everything is known, you get y11. Then you put this y11 here again, that's equal to y12. Again substitute this y12 is substituted in the given equation, you will get y13. So on and so forth. You get all these n approximations only for the first value y1. So why it is called modified Euler's method? Why it is called modified Euler's method? For two ways. Because this y dash at x0 y0 is there only f of x0, but it is modified as f of x0 y0 plus f of x1 y1 by 2. That is one problem. Second thing is, whatever value we get, final value we get for y1 in Euler's method, using the formula y1 is equal to y0 plus h into x0 y0. And that we are considering as initial approximation in modified Euler's method, and that is now redefined, then redefined and refined using a particular process proposed. So y1n, y2n, y12, y11, y12, y13 are successive approximation to y1 of yx1. y1 is equal to y of x1, and they are given by y1 plus 1 is equal, that is n plus first approximation is equal to a0 plus h by 2 f of an xn by n plus f of xn by n. So this is what we call modified Euler's method. Similarly, now once you get this accuracy achieved at y1, you fix that y1, very good. Then if you want to calculate y2, again start afresh. y1 first be evaluated using Euler's method, you call that as y10, substitute y10 here in Euler's method's formula, then you will get y11, then again y12, then again y13. After finite number of steps, what happens is y1, y2, y2, y3, y4, so on and so forth. They appear to be converging to a fixed value. That will be our root. So what are the important observations here in this modified Euler's method? It gives more accurate results than Euler's method. Obviously, because Euler's method, there is no refinement here. There in Euler's method. In modified Euler's method, what we did? Whatever value you have got in Euler's method, that is considered as initial approximation. and that is improved repeatedly till we reach the required accuracy. Okay, so the difference between Euler and modified Euler methods is Euler method is not iterative method. Euler's method is direct method to get y1, but here see y at x2 is y2 n plus 1 is equal to h1 plus y1 plus h by 2, f of x1 y1 plus f of x2 y2, and y2 n is repeatedly applied this. Okay, so Euler's method is a single step method, direct method, whereas modified Euler's method is iterative method. It modifies the root obtained, solution obtained in Euler's method. The next point is both are single step methods to find y at xn plus 1. Why they are called single step methods? To calculate y xn plus 1, we are using only y xn. We are not going to xn minus 1 or xn minus 2. Just we are using the values of at xn, we are getting the values of y xn plus 1. So that is single step method. Problem. Y dash is equal to x square plus y. Y0 is equal to 1 and y at point 2. Clearly what is the h? Y0 is given. They are asking to find the value at y at 0.02. So what is the difference? H is equal to 0.2. By Euler's 0.02. By Euler's method, y at 0.02, if you call it as y1, then it will be y0, that is y0 plus h is 0.02 into f of x0 y0. This is from Euler's method. So y0 is 1 plus 0.02 into f of x0 y0. x0 is 0, y0 is 1. 0 square plus 1. So this is your y at. So this as take as y10. Take this as y10 for the modified Euler's method. So y10 in the modified method, y1 n plus 1, use the formula y1 n plus 1 is equal to y0 plus h by 2 f of x0 y0 plus f of xn x1 n. So if you put these known values, y0 is 1, h is 0.02 by 2, f of x0 means f of 0, 1, f of x1 y1 n is, x1 is this point that we are discussing now, that is x1 is 0.02, that is x0 plus h, and y1 n is not known but is approximated with y10 from modified Euler method is 1.02. You put it here. So simplify this, you will get y1 2. So y1 1. Okay. Then this is what we get 1.0204. You again put y1 1 here in this. Okay. So you get y1 2. That is y0 plus 0.011 plus f of 02 y11. So put this value here and then you get 1.0202. So y1 I say is almost very close to 1.0202. So this is y1 n. This value of y1 using modified Euler's method. Similarly, you can calculate y2 n also. When we want to calculate y2 n, that means let us say x is equal to 0.04 we want to calculate. At x is equal to 0.04. So y2 is equal to y of x2 is equal to y at 0.04, and you get the value of y1 first from Euler's method. y1 is equal to y2 is equal to y1 plus h into f of x1 y1. Take that as initial approximation for the modified Euler's method. So the process will be repeated. You will get the second approximation, nth approximation for y2 also. Another problem, y dash is equal to minus xy square, y at 0 is equal to 2, find y at 0.1 using h is equal to 0.1. So x0 is 0. Given that x0 is 0, y0 is 2, h is equal to 0.1. So Euler's method, if you use y1 is y0 plus 0.1 into f of x0 y0. So if you calculate x0 is 0, so the whole thing becomes 0. So y1 is equal to y0. y0 is 2. So y1 is 2. So from Euler's method, this you take as y10 in modified Euler's method. So y10 is equal to 2 in modified method. So y1n plus 1 is equal to y0 plus h by 2 f of x0 y0 of x1 y. So for n is equal to 0, you will get y11, y11. So 2 plus, that is y at 0.1. So h by 2 is 0.05 plus f of x0 y0 is 0 because x is 0 plus f of x1 y1. x1 is 0.1 and y1 is, you take this y10, that is 2 square. So if you simplify this, that is 1.98. y12, again 2 plus 0.05 to 0 plus, again in place of y11 is 1.98 square, is 1.9804. Again, you go ahead with n is equal to 2, 3, 4, 5, so on and so forth. You get all the values. As we see that, we observe that this y1n gradually tends to a value 1.94 something. So you will see the observation, the values up to, if you go to n is equal to 4, 5, you will see that the y1n approaches this value uniformly. Similarly, y21, y20, you take this as a starting point for the transient situation. We simplify y1, y21, y22, y23, yn, and you find that you will get this solution approaches to 1.9231 gradually. So that's about modified Euler's method. Then comes the most efficient and most important method, that is called Ranga-Katta methods. These methods are called Ranga-Katta method. There are so many advantages attached to it and so much of theory also attached to it. Why it is so important? All the previous methods have slow convergence rates. All the previous methods have slow convergence rates and involve calculation of higher derivatives. Particularly in Taylor series, if you see, if y of x is equal to y of x naught plus x and h into y dash x naught plus h square by 2 factor y double dash h cube with 3 factor f by triple dash, and goes on till, if you want to go require more accuracy, you have to calculate till y nth derivative of y. For second and third derivative itself, we found it difficult. So the higher order derivative calculation is not that easy. If it's a simple function, okay, but if a complicated function, say for example, I take a function square root of 1 by square root of 1 minus x square. How many times if you integrate, there will be more mistakes. So it's a very laborious process, finding out all the derivatives of different orders, and then it's a laborious process. Ranga-Katta methods require only the values of the function only, not the derivatives. That is the main advantage here. So first let us see what is first order Ranga-Katta method. This is Euler's method. This is nothing but Euler's method is called first order Ranga-Katta method. I'm not explaining because straight away it is Euler's method. It gives you y1 is equal to y0 plus h into f of x0 y0. Coming to second order Ranga-Katta method, it is given by y1 is equal to y0 plus 1 by 2 k1 plus k2. It's also very much close to modified, not very much close, same as modified Euler. There we are using h by 2 into f of x0 y1 plus f of x1 y1. So the same thing. The same thing here. K1 is equal to, this y1 is equal to 1 by 2 k1 plus k2, where k1 is h into f of x0 y0 and k2 is equal to h into f of x0 plus h y0 plus k1. See, k1 is used here. Okay, this k1 is, why it gives better results than this is, it internally calculates the previous values also. See, y1 is in terms of k1 and k2. Okay, what is k1? h of x0 y0. It is Euler's term, the first term in Euler's method. And then we are defining k2. What is k2? Again, the next point x0 plus h and y0 plus k. And we are also finding this K2 also at that point, taking the average of those things. So that gives you a better approximation. So if x0 plus h is equal to x1 and y0 plus k1 is equal to y1, it is same as modified Euler's method. x0 plus 1 is x1, y0 plus k1 is y1. Then it is same as modified Euler's method. So I'm not going to the RK method of order 2 also, because we have done some problems already on modified Euler's method. I am not going into it. Third order RK method is there, but it is not widely used. So in fact, synonymously, if somebody asks you to apply Rangakatta method, it's almost all saying that apply fourth order RK method. Fourth order RK method is so popular. So when I said RK method, in general, people say whenever they say RK method, it means that it is RK method of order 4. Because second order and first order RK methods are modified and Euler's modified method. They don't give great accuracy and computational difficulty is there. So when it is said RK method, it is saying as RK method of order 4. So what it says is, this method is most commonly used method. It is given by y1 is equal to y0 plus 1 by 6 into k1 plus 2k2 plus 2k3 plus k4, where k1 is h into f of x0 y0 plus k2 is equal to h into f of x0 plus h by 2 y0 plus k1, but where k1 is this one, we are using it here, and k3 is h into f of x0 plus h by 2 y0 plus k2 by 2. K2 is this one, this is using here, this one is used here, and K4 is f of x0 plus h, y0 plus K3, this one. So if you observe the K4 in terms of K3, but K3 in terms of K2, K2 in terms of K1. So internally there is an iteration goes on internally, you don't observe that. So finally it gives a very good approximation to the solution. So this is a very, very, very important method. I'm sure you'll get a question or two on this Rangakatta method of order 4. Be very practice more on this. So coming to the problem, if y dash is equal to x square plus y square is the given problem, y at 1 is equal to 1.5. Find y at 1.1. I am not going to first order, second order, third order of RK because they are all on first and second order. We have done already problems, so I am not going to it. Third order I am not all touching because it's not advisable for different reasons. So I go directly to RK of fourth order. So this is x square plus y square, y at 1 is 1.5. So h is clearly 0.1. So k1 is h is equal to f of x0 y0. So x0 is 1, y0 is 1.5. If you substitute here, 1 square plus 1.5 square into h is 0.1. Why h is 0.1? Because in the condition it is given as y at 1. And what is asked? Y at 1.1. So h is, you can take 0.1. So k1 is equal to h into f of x0, well, this is what we get, 0.325. So k2 is equal to h into f of x0 plus h by 2. x0 is 1, h is 0.1 by 2, 0.05. So 1 plus 0.05 whole square plus y0 plus k1 by 2. y0 is 1.5 plus k1 is 0.325 by 2. That comes to be 0.1625 whole square. If you calculate the value of this, you get 0.3866. K3 is f of x0 plus h by 2, y0 plus k by 2. Okay, where x0 and h, y0 are given to you. Uh, 1 plus 0.5 whole square plus 1.5, 1 plus 1.33 whole square. So if you simplify this, you will get K3, and in K4 we get again, we use this K3, and that is given as K4 is equal to h into f of x0 plus h plus y0 plus K3. So if you simplify that, 1.4808, then using the fourth order RK method, y1 is equal to 1 y0 plus 1 by 6 k1 plus 2k2 plus 2k3 plus k4. You get the value as 1.8955. So another problem, y dash is equal to y minus x by y plus x, y at 0 is equal to 1. So find y at 0.2. When I ask you y at 0.2, h is clearly 0.2. So x naught is the problem given as 0, y naught is 1. Everything is clear now. So k1 is equal to h into f of x naught y naught. H is 0.2 into f of x naught y naught means y naught minus x naught by y naught plus x naught. Y naught is 1, x naught is 0. So 1 by 1, that is 1. K2 is h into f of x naught plus h by 2, y naught plus k1 by 2. H is 0.2, f of x naught is 0 plus h is 0.2 by 2, that is 0.1. That means f of x naught plus h by 2 becomes 0.1. Okay, y naught plus k1 by 2, y naught is 2, y naught is 1 plus k1 is 0.2 by 2. So if you use this formula carefully, then we get about 0.2 into 1 by 1.2, that comes out to be 1.1666. So K3 is now f of x naught plus h by 2, x naught is 0, h by 2 is 0.1, f of 0.1, comma y naught is 1 plus K2 by 2, this by 2. So you get 0.16619. Similarly get the value of K4, you get 0.07072. Then y1 is the weighted average of these things plus y naught. Y naught is 1 by 6, k1 plus 2k2 plus 2k3 plus k4. We get y at 0.2 is equal to 1.15607. So till now we have discussed only single step method. Here also what we are doing, y in method also. Y1, when we want y1, we are using x naught, y naught. Of course, x naught plus h by, these are dummy variables. X naught, y naught only we are using. When you want to calculate y2, we are calculating x2 and y2 only. So that's also a single step method. And coming to the multi-step methods, we have methods called very popular method that's called predictor and corrector methods. We have very popular methods, predictor and corrector methods. What we do there in predictor and corrector methods is, using previous values of the y, first we predict something and then we correct it using another set of conditions. So what is that? Milne's predictor and corrector method. In this method, 4 values of previously calculated values of the dependent variable y and y dash are used in subsequent steps. So previous 4 values we consider to get both predictor and corrector method to get the solution of the given differential equation. So let us say the differential equation y dash is equal to f of x, y is equal to y x naught is equal to y naught is given. So then predictor formula is given by yn plus 1 is equal to yn minus 3. See how many values we are considering. Yn plus 1 I want. So coming from here, yn minus 1, yn minus 2, yn minus 3. How many previous steps we are considering? For yn plus 1, yn minus 1, yn minus 2 and yn minus 3. So previous 4 level values we are considering, 4 values of the y at different levels. So that's why it is called multi-step method. In the corrector method also, if you see yn plus 1 is characterized in terms of, here also yn plus 1 is also considered, yn minus 1 and yn minus 1 here also. Okay, so that's why these methods are called multi-step, and we don't need much of interaction more than this. That's enough. So straight away we go to problems. Y dash minus 4y is equal to 0. Y of 0, you call it as y naught is equal to 1. And that means, see, all the 4 values will be given to you. You have to get the present value or next value. So y1 that is y at 0.1 is given to you, 1.492. y2 is given to you. y3 is given to you. So you have to calculate y4 onwards. Y4 onwards. First, let us see predictor formula. F of xy is equal to y dash is equal to 4y. Because this equation is given as y dash is equal to y dash means 4y is equal to 0, or y dash, if you compare this with y dash is equal to 4x for f of xy, your f of xy is equal to 4y. So h is equal to 0.1 because y at 0, y at 0.1, y at 0.2, y at 0.3 are given. So h is equal to 0.1. So x naught is 0. Okay, x2 is equal to 0.1, 0.2, 0.3, so on and so forth. So this is the data we have. And one more thing we have to use here is, what is this YNI? YNI is the functional value at this x and yn. So same as f of x and yn. Okay. So predictive method, first predictive method is yn plus 1 is equal to yn minus 3 plus 4h by 3 into 2in minus 2 minus yn minus 1 plus 2yn. I am using this formula. So y for n is equal to, because here if you put n is equal to, the values are given to y0, y1, y2, y3 are given. y3 is also given. That means what is y3? After y3 what comes? y4. The formula is given as yn plus 1. I want y4. So what should be the value of n? 3. So if you put n is equal to 3, you get y4 is equal to yn minus 3 0 plus 4h by 3 2y1i minus y2i, because n is equal to 3, plus 2y3i. So y1 is function value 4 into y1. y1i superscript i. So that is given by 4 y1 the function value. y2y is the function value at y2 8.904, and y3i is function value at y3, that is 4 into 3.22, that is comes out to be 13.28. So if you get substitute all this formula here, expressions here, y4 becomes yn minus 3. Yn minus 3 is given to you in the problem. Yn minus 3 ante n is 3, no, y0. What is y0? Given 1. Plus 4 into h is 0.1 by 3, 2yn minus 2. n minus 2 means n is 3. So n minus 2 is 1. y1i is 5.962. Okay. N minus yn minus 1i. yn minus 1 is y2. y1 is 3y. So if you substitute these values, we get y4 is 4.9456. See, this is the predicted value. This is the predicted value, and it may have some errors. So we correct this by using corrector formula. What is corrector formula? yn plus 1 is equal to yn minus 1 plus h by 3 into yn minus 1i plus 4in plus 4in plus 1, where y4 is equal to y2 plus h by 3 into this the calculations already we have done here. So that comes out to be 4.95288. Here, what is the predicted value? 4.9456. It is further corrected as 4.95288. This is called a multi-step method. Why? Because to calculate yn plus 1, we are using yn minus 1, yn minus 2, and yn minus 3. 4 different values of y we are calculating. So that's why it's called multi-step method. In fact, that is the most important method we have in the curriculum, undergraduate level curriculum. But higher level, we have so many methods to solve ordinary differential equations, to solve what is that numerical integration, or maybe solutions or root solving. There are so many hundreds of methods, but this is what we have undergraduate level. Now let us see what top 5 questions we are getting in GATE. Okay. So the first question in 2020, integral 0 to 1 5x cube plus 4x square plus 3x plus 2x is estimated numerically using three alternative methods, namely rectangular, trapezoidal, and Simpson's rule with common step size. In this context, which one of the following statement is true? C. Three alternative methods, namely rectangular, trapezoidal, and Simpson's rules. Simpson's rule as well as rectangular rule of estimation will give a non-zero error. No, I cannot say. Only Simpson's rule of estimation will give zero error. Simpson's rule, rectangular rule as well as trapezoidal rule of estimation will give a non-zero error. Not possible. Only rectangular rule of estimation will give a zero error. No way. So answer is clearly B. Because why? Because Simpson's rule, what we are doing is, we are using a third degree polynomial, Simpson's 3/8 rule. So these are the third degree polynomial. By estimating this with 3/8 rule, we get a close approximation. A continuous function f of x is defined if the third derivative of xi to be computed, because that is interpolation, we don't have that. Yes. The value of the integral 0 to 1 to 25 f of x dx using Simpson's 1/3 rule. 1/3 rule means we have even number of subintervals. This is how many we have. This is 1, 2, 3, 4. Okay, and the rule is very much given to you. You can 4 into y2 plus y4 plus 2 into this thing y3 plus y5, you get this value of 241.6. The evaluation of the definite integral minus 1 to 1.4 x mod x by using Simpson's 1/3 rule with step size h is equal to 0.6. See, this is a tough problem. So the Simpson's 1/3 rule is h by 3 y0 plus yn plus twice y2 plus so on and so forth by n minus 2 plus 4 into y1 plus y3. So if you call them as y0, y1, y2, y3 and y4, okay, y0 plus y4 will be there here, 2 into y2, that is the only term that we have, and 4 into y1 with 3, y, this is y1 and this is y3. And fx is equal to x mod x. So if you put different values, the h is equal to 0.6 and start with minus 1. So the first value is x is equal to minus 1. The second one is if you add 0.6, that will minus 4, minus 0.4, plus 2, plus 8 and 1.4. These are the values we get. At minus 1, this is minus 1, modulus of minus 1 is 1 into minus 1. Then minus 0.4 is minus 0.16. 0.8, it comes to 0.64. 1.4, 1.96. So if we substitute the values in here, integration, this is what we get, 0.592. That is, the answer is B. For the integral 0 to pi by 2 8 plus 4 cos x dx, the absolute percentage error in the numerical evaluation of the trapezoidal rule using only one endpoint is, so 0 to pi by 2 8 plus 4 cos x dx, fx is equal to x naught is equal to, and only one endpoint means 0 and pi by 2. H is pi by 2. That means we are taking 0 and pi only one step point. So that means this integral becomes h by 2 into f naught plus fn. Okay. So 4 pi plus 4. So approximate value integrated by trapezoidal rule is h by 2 into f naught plus fn. In between we don't have any terms. So f naught is 8 plus 4 cos 0. So this is value we get, pi by 4 into 20, that is 5 pi. But absolute percentage is true error minus approximate value by true value. That is, the actual integral of this is, if you can calculate that, that value minus this 5 pi by the true value in 100%, that is called 5.2%. So that means you have to integrate this first 8 plus 4 cos x, 8x plus 4 sin x between 0 to pi by 2. If you evaluate the integral, it is 4 pi plus 4. If you apply trapezoidal rule, this is, the value is 5 pi. 5 pi and 4 pi plus 4. So 4 pi plus 4 minus 5 pi, that is true value minus approximate value, where true value is 4 pi plus 4. So it comes out to be 4 minus pi by 4 into pi plus 4. Or if you simplify that, it comes out to be 5.2%. So in R19, GATE 2019, Newton-Raphson used to determine the root of the equation fx is equal to e power minus x minus x. The initial guess of the root is 0. The estimate of the root after 2 iterations. So don't think, once again I am telling you, the problems we are doing in this 2 hours class are very lengthy. What he is asking is, if you start with initial approximation as 0, what is the estimate after 2 iterations? The estimate of the root after 2 iterations, that means you have to calculate x1 and then x2. What is the second approximation, second iteration for the root? So that is, formula is xn plus 1 is equal to xn minus f of x1 by f dash xn. So first you find the function value f of x, f dash x at 0, you will get x1. Using x2, you will get x2. Using x1, you will get x2. You have to get the value of that. So numerical problems, I think in numerical is mostly you are getting on numerical integration. So we have to be very careful with numerical integration. Again, one more problem on numerical integration. Integral 2 to 4 x to dx using a 2 equal segment trapezoidal rule. 2 segments only, equal segments. That means it should be 2, 3, 4. Because integral from 2 to 4, 2 to 3 and 3 to 4 only 2 equal segments. So very easily you can calculate h by 2 into h is 1, then 2, 3, 4, h is 1. So 1 by 2 into y0 plus y2, you call it as y0 as 2, y1, x0 as 2, x1 is 3, x2 is 4. So 1 by 3, 1 by 2 into y0 plus y2 plus 2y1. If you calculate, that is the answer. The derivative of fx is equal to cos x can be estimated using approximation f dash x is equal to cos x f of x plus h minus f of x minus h by 2h. The percentage error. The derivative of f of x at pi by 6. You calculate this using this formula, h is equal to 0.1 if you take. So f of x plus 0.1 minus f of x minus 0.1 by 2 into 0.1. If you use this formula, you get approximate value. But you know what is the derivative of f dash x? F dash x is minus sin x. Minus sin x at pi by 6. So difference between these two by exact value, you calculate this, will be finding out the value whether it is less than 0.1% or greater than 0.1%, so on and so forth. The values of a function fx over the interval 0 to 4 are given to you. Then according to trapezoidal rule, what is 0 to 4 f of h dx? Just by you can calculate orally. F h by h is, what is h is? H is 1. So 1 by 2 into 1 plus the last value 1.06 plus 2 into the remaining values. So 0.2, 0.5 plus 0.2, 0.7 plus 1, 0.8 into 2, 1.6 plus 1.16. So 2.76. 2.76 by 2. You get 1.3 something like this. So variation of water depth y in gradually varied open channel flow is given by the first order differential equations also. So given the initial condition y at x is equal to 0 is 0.8 meters. The depth of flow at a downstream section at x is equal to 1 meter from the calculated step of single step Euler's method. Single step Euler's method is simple. Yx1 is equal to yx0 plus h into f of x0 y0. x0 is 0, y0 is 0.8. Substitute them in the equation, simplify it using Euler's method. That is what is required there. The quadratic equation 2x square minus 3x plus 3 is equal to 0 is to be solved numerically, starting with an initial approximation x naught is equal to 2. The new estimate of x out the first iteration using Newton-Raphson. Newton-Raphson UGC, you have to get the first approximation. F of x at 2, 8 minus 6, 2 plus 3, 5 by, okay, 5, 1 becomes 1. Just make f of x by f dash x. F of x is 2 into, substitute this 2 here. X square is 4 into 2, 8, minus 6, 2 plus 3, 5. Numerator is 5. F dash, denominator is f dash. 4x minus 3. At 2, 4x is 8, minus 3 is 5. Numerator is 5, denominator is 5, cancel out 1. So x naught minus that is 2 minus 1 comes 1. The fourth order RK method to solve an ordinary differential equation is given as that formula is given. Okay. For a special case when the function depends only on x, the above RK4 method reduces to. So it is changing only on x. That means these terms will be constant. There is no change. When these things will be constant, what happens? K1 is f of xy, K2 is, and when you close this y at K1, y at, they are not changing. So these two things will be same. F of x plus h by 2 plus f of x plus h. This becomes 4, 2k2 plus k3. These two things become 4k2 plus k3. And last point. Okay. So that comes out to be Simpson's one-third rule. What are the coefficients in Simpson's one-third rule? First term plus last term. Okay. Plus 4 into. That comes out. This method becomes Simpson's one-third rule. An explicit forward Euler method used to numerically integrate the differential equation with a step length of 0.1. Initial condition is y at 0 is 1. Value at y at 1 computed by this method correct to decimal space. My God. See, your job is here now. What is given to you? Y at 0. What is there? He is asking y at 1. Done. It takes minimum 5 minutes time. Y at 1 means what is step length? 0.1. So how many values you have to calculate? Y at 0.1, y at 0.2, y at 0.3, y at 0.4, 0.5, 0.6, 0.7, 0.8, 0.9, 10 values you have to calculate. Okay. If you have such a problem, that's why I'm telling you practice more difficult problems. And if you get a similar problem in the examination, then you can attempt it very easily. But if you practice simple problems, it is very difficult to face the examination. So this is a lengthy problem. Solve the differential equation using second order Runge-Kutta method. That is, second order Runge-Kutta method is nothing but modified Euler's method. dv by dt is equal to t minus root y. The initial condition t at 0 is 4. Use the following RK2 method. Integration is h is equal to 0.5. Okay. So either you can use the second order RK method or modified Euler's method. Consider the equation du by dt is equal to 3t square plus 1. U at 0 is 0. This is numerically solved by using forward Euler method again. Delta t is equal to 2. The absolute error in the solution at the end of the first time step. So that means first we have to calculate the solution using exact solution. That means use as a linear equation. Then find the solution using Euler's method, forward Euler method, get the difference, and then percentage error. So d2 by dx square plus f of xy is equal to 0 is said to be solved using the conditions y at 0 is equal to a, y at 1 is equal to b. Which of the following numerical methods can be used? Euler's with shooting method, no. Euler's with shooting method, without shooting method, no. Both. Yes, it's a boundary value problem. It is a boundary value problem. Similar method, Euler's method, for boundary value problems, we use shooting method. The material numerical method used to find the root of a non-linear algebraic equation that converges quadratically. I told you yesterday, Quadratic convergence, they are asking questions on quadratic convergence and type of convergence. The numerical method used to find the root of a nonlinear algebraic equation that converges quadratically. What is that method we have learned that converges quadratically? Is Newton-Raphson method. So this is the type of questions we are getting. So some more problems we have in numerical methods, not this, sorry. Find a positive root of cut to 3 decimal place by bisection method. Find the positive root of, I upload these problems to you. You practice some problems, whatever you want. They're all Ringakatta method of second order to find the solution at point 1. After the Ringakatta method of second order and third order. Okay, sometimes don't neglect third order, also do it. Sometimes they are asking. Using OS method, solve numerically the y at point 2, point 2, 1, so on and so forth. So all these methods we have discussed. These problems also we have discussed this problem. Okay, practice. Only thing is you have to practice a lot. So with that, numerical methods are completed. And my dear friends, when asking me to about PPTs, I have sent these PPTs till 4th of this month. That means up to partial differential equations. I have already uploaded the PPTs to the university. They have to upload into the portal. Most probably today they will upload it. And the remaining part PPTs of numerical methods I will upload today. Today evening I will upload numerical methods PPTs to the university organizers, and that is their turn to upload into the website. Now we have in the common subjects till now we have completed almost 90% of the syllabus for the common topics in mathematics. So there are 2 more topics. One is if you see the GATE syllabus, the common topics, once I'll show you what we have. This is linear algebra is there for all these branches, chemical, civil, triple mechanics is completed, and calculus is completed, Denmark is completed. Differential equations, we have done all these parts, we have completed, and then numerical methods we have completed, vector analysis, vector calculus we have completed. This is also over. Okay. So the only part that is still we are having is a linear so put it single this thing. Okay. So linear algebra is over, calculus over, differential equations over, probability statistics, and numerical methods and complex variables. So numerical methods is also over. So we are left with complex and probability and statistics. In civil also we have linear algebra, calculus, ODE, PDE. Numerical methods is also completed. We are left with probability statistics. CSCIT complete syllabus is completely different. Linear algebra, calculus, these topics are complete for CSC and IT. We have discrete mathematics and probability still there. So linear ECG, linear algebra, calculus, differential equations, vectors, complex analysis, numerical methods, probability statistics. Here also we have complex and probability statistics pending. So triple E also all the topics are over except complex variables and probability and statistics transform theory. Mechanical also all these topics are completed except complex variables and probability statistics. So if you look at the as a overall, only common topics which are not yet covered are complex variables and probability statistics. So that's why today we'll start complex variables. Yes. So we have done some introduction of, we have learned what is a complex variable. Maybe at intermediate level you have studied, at BTech level also you have studied a bit. So complex number, a number of the form x plus iy is said to be a complex number if x and y are real numbers and I is square root of -1 is called a complex number. I repeat, x plus iy, where x and y are real numbers and I is square root of -1, then x plus iy is said to be called a complex number. And then x is called real part and y is called integral part of the complex number. Geometrical meaning is very important for complex variables. We come across this geometrical meaning of this in Cauchy integrals and all that. Every complex number x plus iy can be expressed as a point xy in this complex plane, and we call that place as Argand diagram. Argand diagram. This pxy, a complex number x plus iy, can always expressed as p of xy. X is real part and y-axis we call it the imaginary axis. That's why this is differently named as Argand diagram. So if you join this point p of xy with the horizon, and if it makes an angle theta, and you drop a perpendicular on the x-axis, then now if you call this as A, this is O, then we have a triangle, right angle triangle OAP. So cos theta is x by r, sin theta is y by r. Or x is equal to r cos theta and y is equal to r sin theta, and x plus iy, a complex number, becomes r into cos theta plus I sin theta. These are all basic understandings. So because x is equal to r cos theta, y is equal to r sin theta, square and add them, x square plus y square is equal to r square, where r is equal to square root of x square plus y square. That means the distance of this p from O, that is r square root of x square plus y square, and theta is tan inverse y by x. So that means if x square plus y square is equal to r square, what does it represent? In geometry, basic geometry, it represents circle with radius r. If r is a constant, then x square plus y square is equal to r square represents a circle equation, and this xy is a point on the circle. Xy is a point on the circle. X square plus y square is equal to a square. Okay, this is what we mean. R is called the magnitude of x plus iy. This is nothing but in geometrical sense, this is called distance of this OP, and denoted by modulus of x plus iy, and theta is called the argument of x plus y, that is denoted by argument of x plus iy. Some basic principles that we require. I am not going very deeply into the basic results, because whatever we need to our study in complex variables, I am as and when they are required, I will push them to you. So if Z1 and Z2 are two complex numbers, the basic things are modulus of Z1 plus Z2 is less than or equal to mod Z1 plus mod Z2, and mod Z1 minus Z2 is greater than or equal to mod Z1 minus mod Z2. Then De Moivre's theorem is very important. You have studied in intermediate level. If n is a rational number, then it is cos theta plus I sin theta whole power n is equal to cos n theta plus I sin n theta. This is what we call cis theta. Cos theta plus I sin theta is called cis theta, CIS, cis theta. Cis means C and IS. I is imaginary part, yes, CIS, cos theta plus I sin theta. Then functions of a complex plane. Let D be a set of complex numbers, and I take any number from the complex set of complex numbers D. If we have a unique value W assigned to each member of the set D. So take any member from set D, and if you correspond to that point, that element, if you can assign a value, complex value W, then it's called a complex valued function. W is equal to f of z. D is the domain of W, and here z is equal to x plus iy is a complex variable, and W is equal to f of z. And if you call it as u of xy plus I into v of xy, where uxy and vxy are real valued functions. Uxy and vxy are real imaginary parts of f. These are all basic things. So f of z is equal to z square minus 3z, and find the real imaginary parts of that. Z is x plus iy. If you whole square minus 3 into z, then this is x square minus y square plus 2xy I minus 3 into x plus iy. If you separate these items, then x square minus y square minus 3x is your real part, plus I into 2xy minus 3y is the imaginary part. So some basis definitions for that we require for complex calculus and integral calculus, complex differentiation and integration. So in real number systems, we consider intervals we have studied. So what is that neighborhood? Means a minus epsilon, a plus epsilon. If you take a point A and both sides slightly, if you extend this point, stretch it like this, a minus epsilon, a plus epsilon, we are calling it a neighborhood. And what is a similar concept in the complex number system is complex variables, is complex functions rather. Some basic definitions. Circle. If z is equal to x plus iy and z naught is equal to x naught plus iy naught, then modulus of z minus z naught is equal to a, represents a circle centered at x naught y naught and radius a. What is z minus z naught? So real parts x minus x naught plus I into y minus y naught. Then what is magnitude of that? X minus x naught whole square plus y minus y naught whole square under root. If you square both sides, x minus x naught square plus y minus y naught square is equal to a square. What is that? That is the equation of the circle centered at x naught y naught and radius a. Okay. So neighborhood. The set of all points z such that mod z minus z naught less than delta, the delta is positive, is called a neighborhood. Nothing so serious about this. You take a point, a small point here in z plane, okay, consider a small circle, very small circle around that point with radius delta, okay, just like this. If this is z naught, you consider a small circle here, maybe less than delta, whatever it is, a, whatever call it is. Then this interior of this circle is called the neighborhood of z naught. That means z naught, the neighboring points are, if you consider all the neighboring points within the delta radius circle, that is called neighborhood. So mod z minus z naught less than delta is also called as delta open disk, because delta is radius and open disk means here less than delta. If it is less than or equal to, we call it a closed disk. Then deleted neighborhood of a point. But neighborhood means if z naught is there, neighborhood means all the surrounding points within the circle of radius delta, we are calling it as a neighborhood. But we need every such point in the circle, but we don't want this z naught. Then that is called deleted neighborhood. Deleted neighborhood of a point z naught is a set of all points z such that mod z minus z naught is less than delta, but z is not equal to z naught. Except z naught, consider all points. It is called deleted neighborhood of z naught. Then, what we mean by W is equal to f of z? We have used this W is equal to f of z and then u plus iv plus ux y plus iv xy and all that. What exactly we mean here? Let's say this is z plane. Okay, I consider a point x naught y naught. Okay, and a small region around that point, there's neighborhood around that point, and I define W is equal to f of z, which is equal to u of xy plus iv into xy. So z naught means x naught y naught. If you substitute this x naught y naught in u v, okay, u is a function of xy, v is a function of xy, and x is equal to x naught and y is equal to y naught is a point in xy plane. So substitute this here. What happens? You will get new values of u and v. You get new values of u and v. Now you formulate another coordinate system with u axis and v axis. Whatever you are getting out substituting this z naught, that is x naught y naught in these functions, you get uv. So you call that point as w naught. So what is happening? This z naught, then substitute in u and v, where f is equal to u plus iv, we are getting a new point in uv plane called w naught. So this is called w plane. So the function means, complex function means, it's not like a real valued function. Real valued function, if you take x and f of x, x along x axis, and then we get a curve in the xy plane. That's all. But here what happens? We have a z plane which is x axis and y axis, and then you consider the function w is equal to f of z is equal to u plus iv. Then if you substitute the points, that means you get another point, new point here in w plane. Okay. So Similarly, if you consider a small neighborhood around Z0, each and every point inside this circular region is mapped to some other point here, then we get a neighborhood W0 and its neighborhood here. So this is what we mean. So first, after listening to this basic idea of the functions, what are the most important functions in complex variables? Exponential function is the most important thing. If you understand the importance of e power z in complex number, you can do any problem. So e power z, just I'm not giving you any proofs, simply I'm giving the results only. So exponential function is given by e power z is equal, just like in real valued functions, e power z is equal to 1 plus z square by 2 factorial, z cube by 3 factorial, so on and so forth. That is as usual. Then there is a very strong relation always between exponential function and sin x and cosine x. Just like in real variable functions, here also sin z is e power iz minus e power minus iz by 2i, and cos z is equal to e power iz plus e power minus iz by 2. I'm sorry, 2 is missing there. So therefore, if we add these two things, cos z plus iz is equal to e power iz, and cos z minus iz is equal to e power minus iz. So if you put z is equal to xy, if you put z is equal to iy, in fact z is equal to x plus iy, let us say if x is 0, then if you put z is equal to iy in these equations, so e power iy is equal to cos y plus I sin y. Okay. So e power z is equal to e power x plus iy, e power x into cos y plus sin y. So, but x plus iy is, x is r cos theta, y is equal to r sin theta, that becomes x into r into cos theta plus I sin theta. So this is r e power I theta, r e power I theta. Sometimes we compare these two things, e power x becomes r and then y becomes theta. So many things we do in complex variables and functions dealing with complex values. So many things we manipulate, we simplify things and convert into convenient terms using these relations. And e power z is periodic function with period 2 pi. Why? Because e power z is nothing but e power x into cos y plus I sin y. Cos y and sin y are periodic functions with period 2 pi. So the periodicity is not in x, it is in y. Okay. With respect to exponential function, is not periodic. But cos and psi are in terms of y. So this is periodic in y. Right? Y means imaginary part. So e power z is periodic function with period 2 pi I. That's why we write imaginary part here, 2 pi I. This becomes cos 2 pi I plus y is cos y. Sin 2 pi plus y is sin y. So this is same as cos 2 pi plus y plus I into sin 2 pi plus y. So the periodicity of this e power z becomes 2 pi I. And some other important, sin x is I sin hx, and cos ix cos hx, and tan ix is I tan hx, and sin hix is I sin x, and these things are what we call similar. Cos I is asymmetric, cos hix is cos x, and tan hix is tan x. Coming to limits. So the calculus repeats again. Function first we define, then limits, continuity, differentiability, integration. The same lines of calculus wherever you go. Maybe ordinary calculus, partial differentiation and calculus, and then complex integration, complex differentiation. The same thing, complex variables. The same lines they go. Now first we'll talk about limits. That w f of z is said to have limit L, complex number, as z approaches a point z0. If for every real epsilon greater than 0, we can find a positive delta such that whenever fz is very close to L, that is mod z minus L is less than epsilon, then for 0 less than z, mod z minus z not less than delta, then we say that the f of z has, the function f of z has a limit L. We write it as limit z tends to z naught f of z is equal to L. That is, as z tends to z naught in z plane, here like this diagram, if you see, if the z here, I take a z here, right? if I take a point Z here, as Z approaches Z0, and this is f of z. By means of this transformation f is equal to u plus I, we are getting a new point. Okay, as z goes to z0, very close to z0, here this L goes to f of z. That's what we mean by this. As z approaches z0, yes, as z approaches z0 in z plane, f of z approaches L in w plane. That is the relation between, this is in w plane because f of z is in w plane and this is in z plane. In real valued functions, what we have seen is when x tends to x0, we mean that x goes to x0 from the left or from the right. That's why we're calling that as a left limit, right limit, left continuity, right continuity, left derivative, right derivative. We're calling it as x tends to x0 plus, x tends to x0 minus, to represent whether it is approaching from the left or from the right. Okay, but in complex numbers, now in xy plane, not from the left and from the right, we have so many things to consider. So here see, this is zxy, this is x0 y0. Like this, you can have like this, you can have like this, but minimum number of curves required is the jet can come down like this. First path is, this point is x0 y. Okay, this point y is same like this. Okay, then x goes to x0. Otherwise, y from, let us say, some value y to y0, and then x to x0. That is second path. Then join the line between these 2 points. Then this, you can slide along the line like this. That is third path, linear path. The next one is connect these 2 points with a parabola, second degree polynomial, which is second degree polynomial, like this also. So in general it is called in the form y square is equal to max form, x square is equal to may, if this is horizon. Okay, these are the 5 different paths that we study. So this z goes to z0, or else x goes to x0 and y goes to y0. It can happen in different possible ways. Then path 1 is as y goes to y0 and x goes not. The second path is, I repeat the same thing. This should be like this. x0 goes to x0 and x0 goes to x0 and y goes to y0. The second one. Okay, third one is along the straight line connecting this z in z0. Z and z0 connect the straight line and then x approach x0. So y obviously goes to y0. So that is third path. Along the parabolic paths, that means second degree polynomials passing through these 2 points. You can draw a parabola like this, you can draw a parabola like this, then the point is sliding through this parabola connecting these 2 points z0. So most important thing is along any of the paths you have to find the limit. The limit must be unique. The limit must be unique. Then only we say that the limit exists. So it is defined by limit z goes to z0 f of z. Z goes to z0 f of z can happen any ways in the following ways. And we say that the limit exists only when the limit is same in all these cases. Even one case fails, then we say that limit does not exist. Okay. Let us see some limits, results on limits. Limit z goes to z naught f of z exists, and it is unique. Let us say if f of xy is equal to u of xy plus I into v of xy and z is equal to x plus iy and z naught is equal to x naught plus iy naught, then limit goes z naught goes to z naught f of z exists if and only if limit x goes to x naught, y goes to y naught, u of xy is equal to u naught, and limit x goes to x naught, y goes to y naught, v of xy is equal to v naught exist. Then limit z goes to z naught f of z is equal to u naught plus iv naught. Then other limits, limit of f is a, limit of g is m, then limit of a into f plus r minus b into g is al plus r minus bm, and limit of f into g is l into m, limit of f by g is l by m, m not equal to 0. These are the basic properties of limits. Then coming to continuity. A function f of z is said to be continuous at z is equal to z naught if the limit value is equal to the functional value. These are all same as your basic calculus. A function f of z is continuous at z naught if corresponding to each epsilon there exists a delta exists such that mod f of z minus f of z net less than epsilon whenever z minus z naught less than delta. So whenever z naught approaches z naught, then f of z approaches f of z naught. That is what we mean by continuity. F of z is continuous in a domain if it is continuous at every point of that domain. And if f of z and g of z are continuous functions, then f plus or minus g and f into g, f by g, where g of z is not equal to 0, are also continuous. And if f of z is continuous, so is modulus of f of z. So there are some basic properties on limits and continuity. They are very much similar to a one variable calculus. Just I am going through briskly throughout the concepts. But there are some interesting problems. In usual sense, it appears that they behave very finely, but not so finely. What are the anomalies here? Let us see some of the things we have. If f of z is equal to z bar by z bar means z conjugate, continuous at z naught. Is this continuous at z naught? Let us say, let z is equal to x plus iy, so z bar means x minus iy. So if then f of z becomes x minus iy by x plus iy. Yet z is equal to 0, I want. So as z tends to 0 means xy goes to 0 comma 0. So limit z goes to f of 0 means limit x goes to 0, y goes to 0, x minus iy by x plus iy. First let us x goes to 0, substitute x is equal to 0. This becomes minus iy by plus iy. So if you cancel, this becomes 1. So now if you repeat the limit, as I said, the paths, different paths like this or like this. Anyway, limit should be same. So if you observe the second path, that means here x goes to y 0 first and then y goes to 0. Reverse it. First y tends to 0 and x tends to 0. And y tends to 0. These terms will go, iy and y will go. Then becomes x by x. This is 1. What is the limit here? Minus 1. What is the limit here? 1. So limits are not equal. So limit does not exist. And limit does not exist. Why? A function is said to be continuous if limit z tends to z naught f of z exists and equal to f of z naught. Limit itself does not exist. So no question of continuity. So the next one is derivative of f z. I don't want to start it right now because we have 30 seconds short of our time. So let's deal with derivatives, analytic functions, and then line integrals, differentiation, Cauchy-Riemann equation, so on and so forth. What so many things to discuss tomorrow. Tomorrow maximum I want to finish it off. We have today is a 12th class. I have 2 more classes, 13th and 14th. I have to finish it up by day after tomorrow. So I try to finish off complex variables tomorrow, and day after tomorrow we'll see the probability concepts. Thank you. Bye. I sign out.